Okay, so a reactions of aqueous ions topic question. Okay, so this topic's not too hard, guys. Just whack out your flashcards, okay? Flashcards are king for this topic. Just remember all your equations you need to know, all of the color changes, observations, all that good stuff. Now, when it comes onto the ions that you need to know, there's only two 2+ ions and only two 3+ ions that we need to know, okay? For the 2+, all you need to know is iron 2+ and copper 2+. For the 3+, it's going to be aluminium 3+ and iron 3+, okay? Easy as that. Okay, so let's jump into the question here, 7.1. All right, this is from paper 1, June 2018. If you want to check it out yourself, have a go, see how you do. So when anhydrous aluminium chloride reacts with water, solution Y is formed, okay, that contains a complex aluminium ion Z as well as chloride ions. Give an equation for this reaction. So this should be pretty simple, guys. Anhydrous, the lack of water, okay, so we've got a solid aluminium chloride here. From this topic, what I just told you, you need to know the aluminium 3+ ion, okay? So this right here, this aluminium chloride is naturally going to be AlCl3 due to the 3+ aluminium, and the 1- chloride ions requires 3 of the chloride ions, okay? Now, when it reacts with water, we form a solution here. This solution is a complex, okay? So we know that it's a hexa aqua complex. So pretty simple here. All you're going to do is react those two and then balance everything up. So AlCl3 plus water, okay, we're reacting it with water right here, because going to give us Al, the hexa aqua complex, 3+, plus, now 3 of the chloride ions have been kicked off, so 3Cl minus, and I'm just going to balance up this H2/6 right here. Easy as that, 1 mark in the bag. Okay, so next question then. Give an equation to show how the complex ion Z can act as a Bronsted-Lowry acid, okay, with water. So what's going to happen here is Bronsted-Lowry acid, acids and bases topic, okay, it's going to be a proton donor. So how can this right here, this complex that we formed, how can this act as a proton donor? Okay guys, so 3+ ions. Within this topic, you need to know that the 3+ ion complexes are more acidic, or they have greater acidity than the 2+ ions, okay? And that's because the 3+ metal ions have a higher charge density. I'll sort of demonstrate that here, okay? Say we have our aluminium right here, and obviously you have your 6 monodentate ligands coming off, all right? What I'm going to do is I'm just going to draw one of the water molecules, okay? So we got our O here. This is a dative covalent bond right here, coordinate bond. Then we've got our 2 covalent bonds of the oxygen and the hydrogen bonds right here, okay? What happens is, due to this being a 3+ charge rather than a 2+ ion, this ultimately leads to this bond right here weakening, okay? So what happens is this 3+ charge, due to it having a higher charge density, is pulling the electrons within this covalent bond towards itself and weakening the bond. So think of it like boop, 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 is pulling that towards itself due to the increased positive charge on this central ion, okay? And that's essentially how it works. Now, it doesn't completely break the bond. However, it just simply weakens it so that this water molecule is more likely to be able to donate it and give it up in a reaction. And that's essentially the theory behind this. Do your best to remember that. Okay, so what we're going to have here is we're just going to have our complex, okay, our aluminium hexa aqua complex. This is going to react as an acid with water, okay, and give up a proton. Easy as that, okay? So one of these water molecules, one of these 6 water molecules is going to lose one of their protons, okay? So if I write that in, we're going to get 5 water molecules, okay, and 1 OH minus, okay? Now, our charge is going to ultimately change here because we've lost a 3+, we've lost a 1+ proton. So this is going to go down to a 2+ charge. And then this water is going to become a hydronium ion, okay, a H3O+. Okay, so another mark in the bag there. As I said, all these equations, flashcards, guys. So we've got some observations going on here. Next question, describe 2 observations you would make when an excess of sodium carbonate solution, okay, that's important. So we've got our carbonate reactions occurring here, is added to solution Y. Give an equation for the reaction. In your equation, include the formula of each complex aluminium species. Okay guys, so because this is a 3+ ion, within this topic, the 2+ ions are going to react differently with carbonates, okay, than the 3+ ions, okay? The 2+ ions will always form a carbonate, a solid carbonate precipitate. For example, copper 2+ is going to form copper carbonate. However, with the 3+ ions, okay, we also form a precipitate, but carbon dioxide gas is also formed. So one of our observations that I can just chuck in right here is effervescence, all right, the classic effervescence for the production of carbon dioxide, okay? So what I'm going to do is I'm going to go back to our equation quickly of our aluminium solution Y complex, okay, our hexa-aqua aluminium complex. Okay, so this is going to react with carbonate. Obviously, we can just show the carbonate ion rather than the sodium required here as a spectator ion. That's all good to get rid of that. And this is going to form this guy right here, okay? We're going to have our aluminium with our 3 water molecules and our 3 OH, okay? And that's what's going to happen here. Now, AQA is really weird about this, guys, okay? Because this ultimately doesn't have a charge now, okay? Because we've gone from a 3+, we've got 3 OH- ions on here, because this is all to do with acidity, okay? This is giving up protons. 3 of these water ligands are giving up protons, okay? So what happens here is this leads to a neutral charge, but for whatever reason, AQA requires square brackets around this, okay? Don't ask me why. Normally when a complex doesn't contain a charge, we can simply leave the square brackets off, okay? And obviously, like I said, we're going to have our CO2 right here, and water is also always going to be given off, okay? So if we balance this up quickly, all right, we're going to be having 3 carbonates here, 3 carbon dioxides here, 2 of these guys, 2 of these guys, and then 3 of these guys, okay? The reason that I did this is you can balance it up on the fly, okay? But what I personally recommend is just memorizing the equations for this, okay? So I'm going to switch that up a bit. Remember the equations, okay, in this topic. Flashcards are your best friend. I'm just going to keep repeating that, but it's literally the truth, okay? How many marks are here? Look, 1, 2, 5, 9 marks, all right? Now, 9 marks, easy peasy. If you just remember your flashcards, 9 marks in the bag. All right, so that's our first point here. Now, this right here, this guy right here, this is a solid precipitate, and it's a white precipitate. Okay, if you do your flashcards, you'll be all good to go. Okay, so 3 more marks right there. Okay, 2 marks for the observations, 1 for the equation. Okay, next question, 7.4. Aqueous potassium hydroxide. So we're adding in some hydroxide here. Until in excess, that's really important. We're adding it to our hexa-aqua complex solution Y. Describe 2 observations you would make. For each observation, give an equation for the reaction that occurs. In your equation, include the formula of each complex. Okay, easy peasy. 4 marks here, guys. Not too bad. Okay, so under this topic, you really need to be aware of the case where we're adding hydroxides in, okay? There's going to be 2 cases. We're adding limiting hydroxides, and then we're adding excess hydroxide. And that will determine which equation takes place and which observation is there, okay? So our first observation is actually going to be the case where we lead to our acid-base reactions, okay? And this is going to be in the presence of the limiting hydroxide ion, because we're going to add this in bit by bit, okay? And then ultimately, once it's limited, we're going to be adding the excess portion and doing that equation after. Okay, so what's going to happen first is we're going to get our precipitate formed, okay? Again, white precipitate. Hopefully pretty easy to remember that here. Now, what's our equation going to be? Our equation is going to simply be our hexa-aqua complex, as always, our solution Y right here. We're going to react that with a limiting amount of the hydroxide ion, okay? Now, what's going to happen here is we're going to form essentially exact same thing that happened here, but it's with a hydroxide ion instead of a carbonate ion. So not too bad here. And obviously we don't get carbon dioxide given off because there's no carbonates present. It's just water given off. Okay, so this is going to be aluminium H2O3 OH3. And then obviously, like I said, it's going to be 3 H2Os going off here. Okay, now that's done. What we need to do is we need to chuck in more hydroxide so that it's in excess. And what's going to happen here is simply this precipitate is going to dissolve, okay? And it's going to form a new aqueous complex. Okay, so I'm going to say our white precipitate dissolves Easy as that, guys. So what's our equation going to be? So we're going to be starting off with this right here. I'm actually going to add the square brackets back in just so you guys make sure that you do that yourself. Like I said, AQA really likes to see that. So aluminium H2O3, OH3, square bracket that up. Now we're adding it with excess, okay? So we're going to chuck one more of those guys in here. And this is going to lead to the formation of this guy. So we're going to have our OH4 1- complex here, and then 3 H2Os kicked off. So that's 4 nice marks right there, okay? Easy marks, guys. Like, I'm going to keep saying it, but flashcards are king for this topic. Very similar to transition metals, okay? And the test for ions. So all the test tube reactions, flashcards, okay? Aldehydes, toluenes, all that good stuff, flashcards, okay? Now, alternatively, what you can do here is instead of saying the white precipitate dissolves, you can simply just say what the color of the new solution is going to be. This aqueous right here, this is a colorless solution, okay? So that's essentially what happens. Our white precipitate dissolves to give back a colorless solution. So that's the end of the video, guys. So yeah, if you did learn something, if you found it useful, be sure to like the video, subscribe for future maths and science content. It really helps the channel grow. Best of luck in your exams, guys. Peace.